Welcome to the Problems Channel Season 2, Episode 38, the episode which I titled The Area of the Reuleaux Triangle, because in this episode we will do precisely that. We will compute the area of the Reuleaux Triangle. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailer section, find the episode titled The Problems Channel How To. Watch that episode in its entirety, follow all the instructions that were given that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E38, every other vertex of a regular hexagon, designated over here with the lowercase letter h, plays the role of the center of a circle, the length of whose radius is equal to the length of the shortest diagonal of a regular hexagon h. In other words, if we pick, for example, for the first vertex, this point over here, we skip this one, pick the second vertex over here, skip this one, and pick the third vertex over here. These 3 points play the roles of the centers of a circle whose radius, the length of whose radius is equal to the length of the shorter diagonal, shown over here, and over here. The challenge in this problem is to compute the area, the planar area, trapped in the intersection of these 3 circles, and express that area as a function of a, which is the length of a side of a regular hexagon h. Because right now we're studying the mechanics of the divide and conquer problem solving approach in a dedicated manner, the intended solution of this problem should include the portrayal, or should include the description of how the divide and conquer problem solving approach can be applied to the process of generating a solution for the mathematical problem S2E38. We explained the mechanics of the divide and conquer problem solving approach in the previous episode, the Season 2, Episode 37. So if you missed that episode, it may be a good idea for you to find it and watch it. But in the lightning round, if we want to apply the divide and conquer problem solving approach to the process of generating a solution for this or that technical problem, then we should try to carry out the following 3 steps. Step number 1, we want to identify a hole and see if we can divide or partition that hole into a number of smaller and simpler or primitive parts. Once that is done, we should try to carry out the second step, or we should try to find the solutions of all the primitive parts into which we partitioned the given hole in the previous step. Once that is done, we should try to carry out the third step, which amounts to finding a way to combine the solutions of all the primitive parts into a solution of the whole. As such, how can we apply this problem-solving approach to the process of generating a solution for the problem S2E38? Well, in this case, we are given a planar region that is the result of the intersection of 3 circles that are constructed in a way that was explained in the previous segment. That area is called the Reuleaux triangle, after the French gentleman who first studied it. And if we naturally consider the Reuleaux triangle shown over here, the area hatched in red, as our proverbial hole, then what are the possible ways to partition or divide that hole into smaller and simpler primitive parts? Well, there are actually a number of ways in which we can partition the Reuleaux triangle into some number of smaller and simpler primitive parts. But in our case, it is practically evident that we should partition it in the following way. The first smaller and simpler primitive part should be this triangle over here. I'll highlight the sides over here so you guys can see it better. This one, this side, and this side. We will call this triangle, for example, tau. And that will be our first smaller and simpler primitive parts. And once we have done that, what are the remaining smaller and simpler primitive parts into which we can partition the given whole? Well, evidently, the smaller and simpler primitive parts that remain to be identified are the circular segments. In other words, this area over here, I'll cross hatch it in red so that you can see it better. This area, then this area, this segment, and this segment right here. Which way should it go? It should go this way. So this segment right here, these are the three circular segments which comprise the remaining three smaller and simpler primitive parts. Let us call one of these circular segments sigma over here. And in the next segment, we will show that all these circular segments, this one, and this one, are congruent or have exactly the same area. But now we can begin answering the question that was posed in this problem. What is the area of the Reuleaux triangle, and what can we say? Well, we can say that this area is equal to the area of the triangle tau, plus, I'll write it, well, let's say over here, plus what? Plus 3 areas of the circular segment sigma, shown over here. And now we carried out so far 2 steps according to the divide and conquer problem solving approach. We partitioned the given whole, the Reuleaux triangle, into 4 smaller and simpler primitive parts. 1, as we shall prove momentarily, equilateral triangle tau, and 3 circular segments shown over here, this one, and this one. That was the first step of the divide and conquer problem solving approach. The second step of the divide and conquer problem solving approach is to solve each and every smaller and simpler primitive part. What does it mean to solve a smaller and simpler primitive part? In this case, to solve a smaller and simpler primitive part means compute the area of the equilateral triangle tau and the areas of all 3 circular segments as shown over here. And that is precisely what we will do in the next segments. Before we can compute the area of the triangle tau, we want to see if we can say something about the properties of this triangle. And in order to do that, let us try to recover the length of any one side of that triangle. What can we say? Well, let us begin with the very first observation. If we place ourselves into the center of the parent regular hexagon H, and we direct our gaze, let's say, at this vertex, and then we begin rotating, for example, this way, and we make one full revolution, then we will transcribe on the one hand the angle, which one? 2 pi. But on the other hand, how many positive stops will we make? 1, 2, 3, 4, 5, 6. In other words, the magnitude of the central angle within a regular hexagon that subtends any one side of such a hexagon shown over here will be what? It will be 2 pi over 6 or pi over 3 radians. So we know this angle is pi over 3. The magnitude of this angle is pi over 3. Now, the sides of this triangle that subtends one side of a regular hexagon are what? They are the radii of the corresponding circumcircle of our regular hexagon. It means that the lengths of these line segments equal one another. And that means that the corresponding triangle is what? The corresponding triangle is isosceles. And by Euclid's Elements, Book 1, Proposition 5, the famous Pons Asinorum, the magnitudes of the interior angles in such a triangle at the base equal one another. Let's say this angle is x. So what do we have? Pi over 3 plus 2x equal to pi, from where it follows what? From where it follows that x is equal to 1/2 of pi minus pi over 3, which is what? 2/3 over pi times 1/2, exactly again, pi over 3. Pi over 3 radians. So these magnitudes, the magnitudes of these angles, are also pi over 3, and here is pi over 3. And then we're thinking right now what? We're thinking that in order to recover the length of, for example, this line segment, we can use what? There are several ways. One of such ways is, for example, to apply the law of cosines, since we already know the length of one side and the other side of this triangle over here. Then the question is, what is the magnitude of the angle between two immediately adjacent sides of a regular hexagon? In other words, this angle right here. And evidently this angle will be, the magnitude of this angle will be what? It will be precisely 2x. It will be precisely 2x, or 2 pi over 3. In other words, we know the magnitude of this angle is 2 pi over 3. This angle right here. By the law of cosines, what can we say about the length of this line segment? Precisely, the length of this line segment will be what? The square root of a squared plus a squared. This is the square of one side plus the square of the other side, minus 2 times what? The product of the lengths of these sides. But these lengths are the same, a and a, both cases will be minus 2a squared, times the cosine of the magnitude of the angle between them. The cosine of 2 pi, the cosine of 2 pi over 3 can be represented which way? This is cosine of pi minus pi over 3. We remember this identity. The cosine of pi minus theta, for all theta real, is equal to what? Minus cosine of theta. So this will be minus cosine of pi over 3, which is what? 1/2. So it will be negative 1/2. So this times negative 1/2. And we take the square root of all of this. And what do we obtain as the result? As the result, we obtain a squared plus a squared, 2a squared minus 2 times its negative multiplicative inverse, it's 1 plus a squared, 3a squared, square root of all this mess comes out to a square root of 3. And because this a is 1 and the same, we just proved that the triangle shown over here, our first smaller and simpler primitive part of the Reuleaux triangle, is what? This length over here. Let's write it down over here. Use the red chalk. This length over here, we have room over here, let's say this way, will be what? It will be a square root of 3. And that triangle is evidently what? That triangle is equilateral. And can we compute the area of an equilateral triangle? Yes, sure, we can compute the area of an equilateral triangle all day long. And how do we do that? We can, for example, recall the theorem. We can use the Heron's formula, for example. Once we know the length of the side of the triangle, this triangle is equilateral, we can compute semi-perimeter and so on. But perhaps the simpler way is to observe that the area of such a triangle is what? Is a half product of the length of two sides times the sine of the angle between them. And that means that the area of the triangle tau is equal to what? Half product of the lengths of two sides will be what? 3a squared over 2 times the value of the trigonometric function of sine evaluated at what? At the point pi over 3, which is what? Which is square root of 3 over 2. So far, so good. So now let me erase this, so to say, in order to save us some space. And there we have it, the area of the triangle tau, the equilateral triangle, as we just proved, will be 3 times a squared times square root of 3 divided by 4. And we're done with the solution of the very first primitive part, or we're done with computing the area of the equilateral triangle tau. And next we will move on to computing the area of the 3 circular segments, one of which over here we named sigma. At this point, I'm pretty sure that many students will try to compute the area of, for example, this circular segment using certain prepackaged formulas, but here lies the problem. On this channel, even if you manage to carry this calculation through in a brute force manner, you will unfortunately not get any credit, because on this channel we're trying to do precisely the opposite. Before we apply a brute force method to a process of solving of this or that technical problem, we want to think out of the box. We want to find a different way, or at least we want to investigate if there is a different way to do that. And this is precisely what we will do. We will avoid a direct or a brute force attack. And to give you an example, not so long ago, literally a couple days ago, with respect to the date when I was shooting this episode, someone on Quora asked the question about how do you evaluate the following improper integral: arctan squared of 1 over x dx, and some number of people developed a solution by taking this integrand head on. However, my idea was the following: represent the product, represent the square of the inverse trigonometric function known as arctan as a product of two functions, like so. Arctan of something over x times arctan of something over x, and then do what? Then introduce the parameter a, and then introduce the parameter b, and then represent this integral like so, and then differentiate this guy over the parameter a, and then unwind the solution from there. And what is this called? Forget about all these things. Even if you do not know what an improper integral is, what did just happen over here? What just happened over here is the application of the problem-solving approach that we already studied: transform and conquer. As such, as I erase this material and prepare the room for the next segment, think on your own about which transformation can you apply to this contraption over here in order to make the computation of the area of these circular segments straightforward, or as simple as possible, but not simpler. And compare your idea. Let me write this so we do not lose it. And compare your idea to ours. Very well. A maneuver that unlocks as simple as possible but not simpler solution of the remaining part of our problem S2M40 is the following, and you may actually see that precisely that maneuver in the introductory course on the theory of groups, if you will be studying the so-called congruence motions of geometric figures. What we do over here is this: we take our generating triangle, so to speak, the triangle tau. Let's say we take this part to be fixed, this circular segment to be fixed, and then we reflect this triangle with respect to its topmost side over here or this side. So if we reflect this triangle upward, this is what we will have. We will have this copy of the equilateral triangle placed like so. And that copy will bring with it the copy of this circular segment into here. And then what we do is we take this equilateral triangle and then we reflect it with respect to this side over here. You see? Reflect, reflect. This consecutive operation of reflection, called the composition of geometric transformations, and let us analyze the result. The magnitude of the interior angle of every equilateral triangle is what? Pi over 3 or 60 degrees. So if we execute these two reflections, this one and this one, in succession, then what we will have? We will have exactly that, 3 copies of the angle pi over 3, pi over 3, pi over 3. 3 copies of pi over 3 will be what? Exactly pi. This angle over here, this angle will be pi radians of 180 degrees. And what does that mean? That means precisely that what we will have in the end is half circle. This shape over here will be half circle, and the radius of this half circle will be what? Precisely a scaled by square root of 3, precisely the length of this side over here. This is the radius of that circle. And again, you may want to over here, for example, get a little bit into the nuances of when two smooth enough rectifiable curves intersect, then what is the angle between these two curves? Well, the angle between these two curves, when they're smooth enough and they possess the tangent, is measured by the smallest angle between the tangents to these two curves constructed at the point of intersection. So here we may represent our semicircle as the union of 3 arcs and compute the angle between these 3 arcs. And what will we see? Well, this, for example, over here will be what? This will be the projection of the center onto this arc over here. And what is the angle between, for example, this side of the smaller original regular hexagon H and this radius is right here? Well, what we compute, 60 plus 30 is 90 precisely. So this side of this smaller regular hexagon H is tangent to these two arcs actually at one and the same point here, and that means that these two arcs meet each other on the one and the same angle. Likewise, the same reasoning works over here. So what we have here is a genuine half circle. And again, I will not go into the details one more time, but what we have here is a recursive application of the divide and conquer problem solving approach again. This observation may be trivial or of kindergarten variety to some, and in some sense perhaps it is, but what I would suggest is that recall that the Swiss-born mathematician Leonard Euler was an absolute master of taking something that is a childish observation and then creatively spinning it into something that is not childish and not trivial at all. So in some sense, many big happenings in mathematics begin with childish observation. So here the childish observation is what? Our new whole, the semicircle, can be partitioned into what? 1, 2, 3 circular segments and 3 equilateral triangles. It's actually a union of all these parts. And consequently, here look at the convenience. The area of all 3 circular segments, this is precisely what we want to compute, will be given by what? By the difference between the area of the corresponding semicircle or half circle with the radius a times square root of 3 will be what? 3 pi a squared over 2 minus what? In some sense, it is 1/2 of yet another slightly larger half of a regular hexagon. This part right here, this part, but we can represent it as a union of 3 equilateral triangles whose areas we already computed, minus 3 areas of these equilateral triangles, which we know already. But in the original formula for the area of the Reuleaux triangle, we have a tau plus this minus 3 copies. That means that for the area, for the total area of the Reuleaux triangle, we will have what? We will have this minus 2 copies of the generating triangle, equilateral triangle, with the side length of a times square root of 3, which is what? 6 minus 6 a squared square root of 3 divided by 4. This is the area of the Reuleaux triangle here. This is the entire area that we are seeking to find. And what can we do over here? Well, these 2 cancels with these 2, and we have 3. Consequently, 3 over 2a squared can be canceled out. 3 over 2a squared cancels out. And what do we have left? 3 over 2a squared factors out, and we have pi minus what is left over here, square root of 3. And this is precisely the area of our Reuleaux triangle. This one right here, again in words, 3 over 2 times a squared times pi minus square root of 3. Pi is evidently larger than, let me just be sure that pi is numerically strictly larger than square root of 3. Everything over here converges. Our area is strictly positive, and that is how we find the area of the Reuleaux triangle. And the next couple segments will be optional. If you are not interested in what we have to say about the Reuleaux triangle, you can skip forward to a new challenge. But in the next couple segments, we will discuss the idea that the Reuleaux triangle is actually the so-called shape of constant width. Back in the 1980s in Moscow, when I was attending my college prep school, which is in some sense an equivalent of mathematics and physics, Circle as an extracurriculum reading. In that respect, we were giving the book whose name I translated for you in English over here, the 2 authors, Yaglom and Boltansky. The title of the book was Convex Figures. It was published by the publishing houses in Moscow and Leningrad. Back then, in the year of 1951, it has 100, the copy that I have has 140 pages in it, and one chapter in that book is dedicated to the so-called curves of constant width. And this is precisely what the Reuleaux triangle is. It is a curve of constant width. What does it mean? Well, a curve of constant width, many students, when they hear that, they will think about, for example, a circle, which is a natural and probably one of the first candidates that comes to mind. And what that means is the following. From a point at infinity, we bring in one straight line, like so, continuously through the parent plane. And from another point at infinity, parallel to this straight line out of infinity, we bring in another straight line. So this straight line and this straight line are parallel. And we keep moving them over the parent plane in one continuous motion until these straight lines, let me show them, maybe let's say in red, until these straight lines touch the circle at 2 diametrically opposite, evidently, points here and here. What happens now is actually quite interesting. Let's say we take a mechanism that runs across perpendicularly like so, and at this point we weld this crossbar to this parallel straight line, and at this point we weld the crossbar to this parallel straight line. And now what happens is this: we take this contraption and we begin rotating it. It doesn't really matter which way. We can rotate it counterclockwise or clockwise in the parent plane. And what will happen? Well, precisely because a circle is a curve of constant width, what will happen is that the motion will be smooth, continuous. It will be possible, number one. Number two, the contraption, our contraption over here will not change its width. The width that we fixed in our welding experiment will remain the same. In other words, this pair of parallel lines will precisely preserve the distance between them as shown over here, this distance right here, as our contraption rotates in the parent plane about the center. Exactly the same thing actually will happen if we repeat this experiment for the Reuleaux triangle. In other words, if we, let me use, for example, let's say blue for contrast. If we, out of the point at infinity, we bring in one straight line that touches, for example, our Reuleaux triangle here, and out of another point at infinity, we bring another straight line that is parallel to this one that runs somehow over here. I mean, obviously, this is an approximation. I cannot see too well if they're parallel or not. But the idea is this, that this distance right here, this distance, if we weld our contraption here and here, and if we begin rotating our two parallel straight lines, again, about the center, this way, clockwise or counterclockwise, it doesn't really matter. The motion will be possible, first of all, and the distance, this distance between these parallel straight lines will remain one and the same. There are all sorts of animations available out there done with professional software, but it doesn't really take that much of imagination to see played out in your mind's eye. Rotate this contraption around the center of the Reuleaux triangle and envision that the distance between these two blue parallel straight lines will be one and the same. It will not actually change. And perhaps because of that property, the Reuleaux triangle has a number of interesting applications in real life. And the first application that I will show you is that back in the 60s and 70s, the mighty Soviet industry managed to produce a movie projector. And amazingly enough, I had precisely the model that I'm about to show you. In your upper left corner, you will see the title. Where should I write it? Maybe over here. You will see in Russian it's spelled like so. These are funny characters, but in English, for example, it will be this, L-O-O-C-H. That's the model. It's called Luch 2 or Luch 2, and actually Luch, this funny sounding thing, is actually a geometric object known as a ray. Evidently, ray of light, movie projector, and this is precisely the thing. And the device in which the Reuleaux triangle used in this movie projector is the portion that goes into the, let's say, this is your old celluloid movie. The frames go this way, but on the side there are little openings in the celluloid film. So what the Reuleaux triangle-based mechanism did is it went into these openings right here and pulled the celluloid or pulled the film down right in front of the lens in a rapid fashion, and voila, at a specific rate, we have a movie. Please take a look. For the next application of the Reuleaux triangle in real life, the folks who are collecting coins may be interested to know that two countries such as, for example, Bermuda and Canada issued coins that have the shape of the Reuleaux triangle, but of course, as mathematically inclined thinkers, we all understand that such coins are nothing more than approximation of. The next application of the Reuleaux triangle in real life is as practical as decorative architectural elements go. In a few seconds on your screens, you will see the front portion of a famous church in Paris, France, and the decorative elements in the facade of that church. Several such elements have the shape of the Reuleaux triangle, which I highlighted with burgundy arrows. The next application of the Reuleaux triangle in real life is related to the previous one because evidently what you will see in a few seconds is a window in a church building that apparently has the shape of the Reuleaux triangle. But again, as mathematically inclined thinkers, we need to understand, and we do understand, that all these things that relate to Reuleaux triangles in real life are nothing more than an approximation of. And one more application of the Reuleaux triangle in real life. This time comes from the country known as Germany, in the city of Cologne. Apparently it is fairly locally famous tower that has the shape of the Reuleaux triangle. And what that means is the following. Imagine that we construct a right circular cylinder, and then we squish it in such a way that if we cut that cylinder, let's say the cylinder has its vertical axis this way, and then if we cut this cylinder with the plane that is orthogonal or perpendicular to its vertical axis of symmetry, what will result? Precisely the cross section of such an experiment will be exactly an incarnation of a Reuleaux triangle. And here is one view of the tower. And here is another view of the same tower. And now we're done with the mathematical problem S2M40, and we will move on to a new challenge next. Our next challenge will be the mathematical problem S2M41. And in that problem, we'll be looking for at least two proofs of the Heron's formula that is based on the divide and conquer problem solving approach, or the approach that we're studying right now in a dedicated manner. As a refresher, if a triangle, Euclidean planar triangle ABC is given with the side length of A, B, and C is shown over here on your left hand side, then lowercase p stands for the semi-perimeter. That's the sum of lengths of all the sides of a Euclidean triangle divided by 2, and then the area of the triangle ABC is given by the following formula shown over here: square root of the product of four factors: p, the semi-perimeter, p minus a, p minus b, and p minus c. This is the triangle ABC. And again, ideally, we're looking for the proofs that are yours. And if you cannot come up with a proof that we're looking for on your own, but you can take someone else's proof and come up with a convincing story that dissects precisely how the divide and conquer problem solving approach dovetails into that proof, then on this channel you'll get a partial credit. But again, ideally, these two proofs should come from you. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share with you two of my proofs from the problem S2M41.